Standard quantum physics suggests the universe operates like a blur of possibilities. Before a measurement occurs, particles appear to occupy multiple locations at once, a state known as a superposition. Erwin Schrödinger highlighted the absurdity of this math with his famous thought experiment. If the equations are a literal map of reality, then a cat inside a sealed box remains in a state of being both dead and alive until an observer intervenes. These equations are remarkably successful. They are the foundation of almost all modern technology, but they force us into a corner where the physical world seems to defy the most basic rules of logic. These reality-breaking paradoxes exist only because of our insistence that quantum math describes the objects themselves. Mathematician Inge Helland proposes a radical departure, an epistemic framework. In this view, quantum mechanics acts as a rigorous model of an observer's limited knowledge about the world. Helland identifies 6 specific postulates that govern how information is gathered and processed. This framework maintains every existing mathematical law of physics. It simply shifts the perspective, centering the math on the observer's cognitive and statistical limits. Redefining the observer as the core of the equation allows us to resolve century-old paradoxes while keeping the fundamental laws of logic intact. The foundation of this theory rests on theoretical variables, the mathematical markers of what can and cannot be known. Helland defines inaccessible variables as the ultimate underlying state of reality. It is so impossibly complex that no observer can grasp it entirely. From that complexity, we extract accessible variables, specific, measurable slices of information that we can actually perceive and record with precision. Observers are restricted to maximal sets of information. Because of this, you fundamentally cannot focus on 2 unrelated maximum sets of data simultaneously. This mirrors Niels Bohr's concept of complementary variables, where knowing one thing with certainty makes another unknowable. In the case of Schrödinger's cat, the observer lacks the specific accessible variable required to know the cat's status before opening the box. Quantum superpositions represent the observer's state of "I don't know." The cat isn't physically dead and alive at once. The observer simply hasn't accessed the data needed to choose between those 2 states. If quantum mechanics is built on these limits, how does it produce the incredibly precise probability laws we see in the lab? Helland points to the likelihood principle from standard statistics. This principle dictates that all experimental evidence is a function of the statistical likelihood of an outcome. He combines this with a rational epistemic setting. This assumes the observer's choices are perfectly consistent, following the Dutch book principle, a logical rule that prevents a rational person from making a series of contradictory bets that lead to a guaranteed loss. When an observer uses these statistical tools to weigh evidence while maintaining perfect logical consistency, the math collapses into a single specific pattern. This pattern is the Born rule, the formula physicists use to calculate every quantum probability. The Born rule emerges as a mathematical necessity for any rational mind trying to make sense of limited subatomic data. Because Helland's postulates describe the boundaries of knowledge, they apply to any system where an observer must make a choice based on incomplete information, including human psychology. In quantum decision theory, an accessible variable is a final decision, while the inaccessible variable is the massive hidden complexity of the human subconscious. Just like a particle measurement, the human mind struggles to hold 2 unrelated, maximal decisions in focus at the exact same time. This cognitive limit offers a new perspective on the 2022 Nobel Prize-winning Bell experiments, which appear to show the universe violating the principle of local realism. Helland argues the anomaly arises because an observer cannot mentally synthesize a single, consistent statistical model for all the variables in the experiment simultaneously. The mind can process pairs of data points, but it cannot bridge the gap between unrelated, complementary sets of information at the same time. The reality-breaking results of the Bell experiment reveal the strictly bounded capacity of an observer to process complex, contradictory data. From the behavior of electrons to the choices made by the human mind, the same 6 postulates define the boundaries of what we can know. Our view of the universe is defined by these observer postulates. transforming apparent paradoxes into the natural boundaries of human information. Thank you to Shane Persinger for guiding this series. To continue exploring the limits of your own accessible variables, like this video and subscribe to The Explainer.